In this topic, we're going to learn how to solve logarithmic equations. For this, we need to remember how to rewrite from a logarithmic into an exponential form, the logarithmic properties, and to understand that every solution we find, we're going to verify if it's indeed a solution by verifying that the argument of the logarithm can be negative. So, let's follow along. As in any type of equations, what you want to do is to isolate the term that has the variable you want to solve for. So in all of these cases, our variable is inside the logarithm, meaning that what you want to do is isolate the logarithm by using the properties of the espejes that you already know and have been using since forever. So in this case, this logarithm has a 3 multiplying and a 1 adding. So as the hierarchy of operations tells us, the first thing we have to do is to add a plus 1 on both sides of the equation to get this expression. Next, the 3 is multiplying the logarithm, so we have to pass it to the other side, dividing, and 9 over 3 is 3. Lastly, my logarithm is completely isolated, meaning that I can rewrite it in exponential form. And remember that that is found by doing base of the logarithm raised to the exponent equals the argument. From here you can see that we have now a single equation that is completely dependent of the variable x, and this can be easily solved, like 8 equals x plus 3, so x equals 5. Now remember that I told you that we have to verify our answer. To do that, we just have to plug our answer into the logarithm, and if the argument gives us a positive number, then it is in the domain of the function and then it's a solution. If when we evaluate our solution in the argument of the logarithm, it gives us a negative number, that means that the solution is not in the domain of the function and thus is not a solution of the equation. So, if we plug our solution into the logarithm, we can easily verify that the argument is positive, so this is indeed a solution. Next one. Again, notice that the hierarchy of operations for solving equations apply as usual. You have a plus adding and a 2 multiplying, so the rule tells us that first we have to subtract a 4 on both sides of the equation, giving us minus 3. Then the 2 is multiplying, so we have to pass it dividing to the other side. Now we have our logarithm completely isolated, so we can change it into exponential form. So we're going to rewrite. Remember that ln means logarithm base e. So my answer has the form of e to the power of 3 halves minus 3 halves equals x plus 3. So if we finally isolate x, this is minus 3x minus 3 equals x. So this is my solution. Now remember, we have to verify our solution. To do that, I'm going to plug the solution into the logarithm. That is a natural logarithm, and this is e to the power of minus 3 halves minus 3 plus 3. This is ln of e to the power of minus 3 halves. And remember that any number to a number is a positive value, meaning that this argument is positive and thus our solution is indeed a solution. Next exercises. Here I have a couple of logarithms, one on each side of my equation. So I'm going to pass all of the logarithms to one side of the equation. This logarithm is positive, so it passes to the other side as negative. And because I pass everything to the left side, this is equals to 0. Now, these two logarithms are subtracting each other, meaning I can condense them as a quotient expression. From here, this is my logarithm completely isolated, so I can rewrite this in exponential form. So this is base to the power equals the argument. 16 to the power of 0 is 1. And then I can pass my denominator to the other side. And lastly, this x can be passed to the other side, and 2x minus x is 1, so 6 equals x. This is my solution. To verify it, I have to plug it into each and every logarithm that has the variable x. So if I plug it into the first logarithm, this is clearly 2 times 6. This is a positive argument, so it checks out. Next, if I plug it into my second logarithm, this is 6 plus 6. This is obviously a positive number, so it checks out too. So this is indeed a solution. Next one, again, I'm going to pass all my logarithms to one side of my equation. Then by properties, these two logarithms are subtracting each other, meaning that I can condense this as a quotient. And once I have it as a quotient, I have a single logarithm, so I can rewrite it as an exponential form. 19 to the power of 0 equals 15 over minus x plus 4. 19 to the power of 0 is 1. And this is minus x plus 4 equals 15. And if I pass this 4 to the other side, this is 11. And if I multiply everything times minus, this is x equals minus 11. So if I verify my answer, I will see that I only have to plug it in this logarithm because that's the only logarithm that has an x. So this is logarithm base 19 of minus 11 plus 4. This is logarithm of 19 of 15. So this checks out because my argument is positive, meaning this is a solution. Now, what happens here? I have, again, logarithms gonna be passed to one side of my equation. And then I'm gonna condense them as a quotient. So this is, rewriting it in exponential form, is 13 to the power of 0, and this is x squared plus 6x over 20 minus 2x. Now, 13 to the power of 0 is 1. We already know that. So if I have 1 here and I pass the denominator multiplying to the other side, this is going to be 20 minus 2x equals x squared plus 6x. Now, notice this is a quadratic expression, meaning that I'm going to have two different solutions. And how do I find the solution of a quadratic expression? You have to equate your equation to 0. That means passing everything to one side. Simplifying. And then factorizing. Two numbers that multiply give me 20 and added give me 8. That is 10 and 2. So my possible answers are minus 10 and 2. Let's verify those answers. First off, with x equals minus 10. If I plug that answer into my first logarithm, this is minus 10 squared plus, minus 60. And this is 100, logarithm base 13 of 100 minus 60, and this is clearly positive. Next one is logarithm base 13 of 20 minus plus 20. This is obviously positive. 1 plus 20, this is minus 2 times minus 10. So this is logarithm base 13 of 20 plus 20. This is 40. So obviously positive, so this is a solution. Next solution that we have to verify is 2. Logarithm base 13 of 2 squared plus 12. This is obviously positive, so it checks out. Next logarithm, this is 20 minus 4. and this obviously checks out. So both of them, both are solutions. Next one. I have a logarithm here, a logarithm there. So remember, all my logarithms have to be on one side of my equation. This is positive, so it passes to the other side, adding. These two logarithms are adding each other, so I can condense them as a product of its arguments. And now that I have a single logarithm, I can rewrite it in exponential form. This is 2 to the power of 3 equals, I'm going to expand this, x squared minus 12x plus 35. Now remember, this is a quadratic expression, so I have to equate it to 0. This is 8. X squared minus 12x plus 35. So if I pass this 8 to the other side, this is 0 equals x squared minus 12x plus 27. Now, two numbers to solve this, to find the solutions of these equations, just factorize it. So two numbers that multiply give you 27 and added gives you 12. This is minus 9 and minus 3. So my possible solutions are 9 and 3. So let's verify those solutions. First off, x equals 9. I'm going to plug it into my logarithms. 9 minus 7, this is obviously 2, so this is positive, it checks out. Let's check the other logarithm. This is logarithm of 9 minus 5, and this is obviously positive, so it checks out. So that is a solution. And x equals 3, let's verify it again. Let's plug that value into the first logarithm, that is 3 minus 7. Uh-oh, this is clearly negative, so 3 cannot be a solution. So x equals 9 is the only solution. Next one, I have a bunch of logarithms. So remember, as usual, we have to pass all my logarithms to one side of my equation. And notice that these two logarithms are adding each other, meaning that I can condense them as the product of its arguments. And I'm going to pass this logarithm to the left side, so it's going to pass subtracting. Now I have two logarithms subtracting, meaning I can rewrite it as a quotient, and this is x squared plus 9x over 22. Now I can rewrite it because my logarithm is completely isolated, so this is 2 to the power of 0 equals x squared plus 9x over 22. And this is 22 equals x squared plus 9x. Why? Because 2 to the power of 0 is 1, and when you pass this 22 to the left side is 1 times 22, 22. Quadratic expression, meaning that I have to rewrite it as an equality to 0. And now I'm going to factorize. Two numbers that multiply give you 22 and added gives you 9. This is minus 11 plus 2. So my possible solutions are minus 2 and 11. So let's check those answers. First answer is minus 2. And notice that in the moment I plug that solution into the first logarithm, this is a negative argument, meaning that x equals minus 2 cannot be an answer. Now let's check x equals 11. Logarithm base 2 of 11 is positive, it checks out. Let's check the other logarithm. Logarithm base 2 of 11 plus 9, this is clearly positive, so x equals 11 is the only solution. Equations can not have an